Hopefully you were able to answer that question on your own. What kind of forces induce those constant stresses? And it would be a solid, for instance, a plate like this that is being pulled uniformly along the y-axis, being pulled uniformly along the x-axis, and the stress in this direction, what's the stress in the y direction? Can you remember what that was? It was A2. And obviously the stress in the x direction was C2. And then we had that third one. We have minus B2. So draw tau xy correctly. This is a negative shear stress. It looks like it's positive from the undergraduate point of view, but it's negative for our sign convention. It's on the x face going in the minus y direction. That's why it's a minus shear stress. Make sure you understand that perfectly. And then let's just play with this a little bit more. Suppose we had a uniaxial stress such that C2 was 0. We had a stress situation where C2 is 0. What would that mean? Well, if C2 is 0, and then we have no stress in the x direction, and if A2 is non-zero, then we'd have uniaxial stress in the y. Or conversely, if A2 is 0 and C2 is not 0, then we'd have uniaxial normal stress along the other axis. And then if C2 and A2 are 0, but B2 is not 0, then we have a case of pure shear. And we could imagine all of these scenarios for very common structures. We could have a uniaxial stress in one direction, a uniaxial stress in the other direction, a biaxial normal stress, which means that both axes have stress. And then finally, all three could be present, as in our more circle problems, or perhaps just pure shear is present with no normal stresses. So it's all doable, and it's all rooted in that second order polynomial that I described as phi 2.